which might not make much sense, but then I'll try and do a little demo to hopefully demo some of the ideas. Okay, so I'm going to be fast. Erlang OTP. This is where it came from. The 80s, telephone switches, Scandinavia. They wanted to build a language that was good at solving particular problems, high concurrency, massively fault tolerant. And Erlang is what they came up with after experimenting with quite a few other languages. This is Joe Armstrong, who's like the inventor of Erlang. He's a cool guy. And this is what Erlang looks like today. These are kind of... Sorry, was that too quick? There you go, there's Joe. Yeah. And this is what Erlang is kind of all about. This is just a bit of a brain dump of all the words that came into my head when I was thinking about Erlang. The actor model is key amongst them, which is its concurrency model. Lightweight processes is how it achieves that. Asynchronous messaging, it's got really high fault tolerance, but it does that by letting actors or processes crash all the time. And loads of other cool stuff. So I'm going to try and demo some of these ideas now. So I'm just gonna. That's my ending bit of code. Start with some simple code. Can everyone see that, by the way? Is that zoomed in here?
No.
Enough?
Yeah. A little bit more, thank you.
More?
A little bit. Thank you.
Okay. So that's a module in Erlang. It uses the module system, and it's got a simple function called hello world. And it exports that function, the export directive there. So this module is like usable outside of the module. Sorry, I'm just going to fire up an Erlang shell so I can try this out. Oh, I'm already in an Erlang shell, so that's handy. Okay. Oops. Sorry, my typing. There we go. Right. So if I load that code, that just compiles the code that's there, and it means it's ready to go now. And now I can call that. In fact, no, sorry. I'll go back to the code and talk through it a bit. So you'll see that there's a receive call immediately in that hello world function, and that tells the process that's running that function to go away and look in its message box for any messages, and then if any messages match those patterns underneath, so in this case the pattern is just a simple hello, then it'll execute that code, and then it'll recursively call itself to start the loop again, because otherwise it just ends. So that's a simple sort of actor in Erlang. So I need to create a process to run that function now. So I can just do that with, in fact, lar equals spawn demo. Right, hello world. So that's the module name, the function name, any arguments you need to pass. There we go. So and that little return value is a process ID for my process now. So there we go. We've got a process running that function. It's just sat there looking in its message box, but no one's talking to it. If we want to just see that, Erlang comes with this handy process manager, which shows you all the running processes on your system, and I can see somewhere, there we go, demo hello world, somewhere, there we go. And you can even do stuff like trace that, so see what it's getting up to at the moment. A lot of people think Erlang seems a bit like part programming language and part operating system, and it is a bit like that, the Erlang, because it's this process-based approach. The Erlang VM runs these lightweight processes. It's got a lot of tooling that feels a bit like an operating system almost. So, okay, so we've got my process that's being traced. I can't seem to move that window, but never mind. Oh, that's so annoying, it's going to disappear. So now I'm going to send a message to my process. Just with that exclamation mark, that's the send message operator in Erlang. I'm sending it a message hello. And what do you know, it's sort of said hello world. If I switch back to my view there, you can see that it traced out all the stuff that happened. We got some requests and it did stuff. So again, that's an actor in Erlang. So it's literally that simple. You know, you can spawn up a process to run every tiny bit of code, and those things are totally independent. They share no state. There's no shared memory between them. They can only communicate with each other through asynchronous message passing, which is a very nice model. And you might think it sounds a bit like an OO type model, and in many ways it is truer to the spirit of OO in some people's eyes, you know, which was people like Alan Kay should have said it should have been all about the messaging and less about classes and objects and things like that. It's about messaging. And so Erlang's a functional language, but in some ways it's a very true to the spirit of the original OO intentions. Cool. So that's some stuff on processes. I'm now going to try and demonstrate the fault tolerance approach. So I've got another snippet. I'm going to go straight to demo 3. So now we've got our new function. I've expanded my hello world to take a different kind of message. This is a message can be any Erlang term, which is any bit of Erlang data basically. In this case, it's a tuple that's tagged with the word divide, just to tell it what I want it to do with it, and then it's got the dividend and the divisor as like parameters that I'm going to pass. And it's just going to do, obviously, it's just going to do that division and print the result to the screen when I call it. So just a bit of an extension to the original function. But it's also got this guy. He's a supervisor who's going to look after that worker process, and if anything untoward happens, he's going to sort it out. So I'll demo this quickly, hopefully. Save that, and I'll talk a bit more about it in here. Let's see if we can get it working. So, okay, so see. Demo. Cool. And now that I've got a supervisor, and the supervisor starts my worker process, I don't have to remember the process identifier that is created. The supervisor is going to look after this for me. So I just have to say spawn demo, the module name, supervisor, visor, and arguments, which is an empty list. Cool. So now my supervisor started, and if I look in here again, I should hopefully see, yeah, I've got my supervisor process running, and it has started up my worker process, my hello world process. So let's send it some messages. Oh, I took a little liberty as well. I registered the worker process against this name demo, so that it's not reliant on an individual process identifier. So I can now just call things demo hello, and it should say hello world. Cool. And I can say demo divide 10,2. Cool, that's working. So we'll go back and look at this code a little bit now. So no, actually, we'll try another thing. We'll say demo divide 10,0. This looks dangerous, right? So when I do that, the supervisor picks up the fact that the process is crashed, and it tells me the reason, because I also get a little bit of logging from the shell. But my system is still alive, you know. It can still do stuff, and we'll talk about a little bit about what happened there. So everything still works. So yeah, what this guy does is we'll start here. He spawns the worker process, but he spawns it as a linked process, which means that the process that's running the supervisor is now linked to that worker process, and he will receive any error messages or exits that occur from that worker process. So when the worker process crashes, it basically tells him our supervised process because we're linked. It registers it against that name, as we saw. This guy, this is also important. This is what makes it a supervisor, really. I'm telling this process that it should trap exits. So normally when a process gets an exit message, it just dies and propagates that message onto all its linked processes. But in this case, I don't want to pass it on, I want to handle it. So that's what that trap exit does. And then again, it just turns that error message into a normal message that lands in my mailbox as a supervisor. So I can decode that message, just a bit of pattern matching there, and they'll appreciate. And I print out the reason, which I've pulled out of that pattern, and then I just recursively call again, which registers a new worker process against the same name, so that the user of the underlying process doesn't really care that it's crashed and something's gone wrong. He's still got all the functionality that worker provided. So that, in a nutshell, is supervision in Erlang. And in a working Erlang system, you get these complicated hierarchies. Obviously, that's a bit of a naughty example, but you get these, they call them supervision trees, where a supervisor is the parent. The children can be worker processes or other supervisors, which supervise more children and more supervisors. Each supervisor might have different rules about, you know, what it does in the event of errors being trapped and stuff like that. And that's how you build a very robust system that has a lot of crashing processes. And Erlang systems turn out to be really robust. So have I got time to do one more bit of, well, I can do one more thing maybe. The other, no.
No, go for it.
All right. So the other cool thing about Erlang is distribution. So because it takes this approach of everything being a process and not sharing state, it doesn't really care about where those processes are running. It's location transparent, they call it. So if I do get rid of that code and do demo 4, this is just a little bit of a new. It's very similar to the last one. I've just put some more handlers to do some other work in that function. And I'm just going to do start again. So C demo. Right, and if I do spawn, so spawn demo supervisor, the arguments. Cool. So I think my supervisors were in there. Did that work, or did that throw an error? Oh dear. What's going on? Well, maybe I'll call it a day then. I can try that. That was working before. I don't know what's working. Let me just try. Did I not? Let's try again. See. I might not have compiled it properly. Sorry. Fat fingers. Spawn demo supervisor. No arguments. Cool. All right, we're going. So now I'm going to open up a new PowerShell. I'm going to start a new Erlang node. So this is called an Erlang node, and I'm going to give it a cookie, the same as the one I gave the other one. So Erlang nodes that have the same cookie can talk to each other. Basically, that's a security mechanism. That's a pretty simple one. And if I now do netadm ping is the message just to try and identify another node on the network. Node 1 at GBBLL1977. Cool. So when you get a successful ping, it tells you pong. If that had failed, it would have said pang. And if I look at my nodes on my network now, I can see that node 1 knows about node 2. And I can now call, I think, if I get this right, so demo on node 1 at GBBL1977. So this time, instead of just saying the name of the registered process that I want to call, I tell it a tuple of the name of the registered process and the node that I want to run it on. Obviously, both these nodes are on the same machine, but in theory, if anyone wanted to quickly spin up an Erlang node, they could call this one as well. And I send it a message, so let's say hello. So you won't see the output there, but hopefully. Hey, all right. So if anyone has quickly got an Erlang node up and running, you can send me messages. Oh yeah, like Anthony's doing from my other laptop over there. So that's just a quick example of how like Erlang is built for easy distribution, creating these clusters of nodes that can communicate, and and the handy for doing demos like this. That's about it. Erlang's a cool language. Everyone should learn it.